Hello and welcome to another Andy's Workshop project video. In this video we're going to take a look at some Xilinx FPGAs that I bought on eBay. Now it was about 2 years ago now. I was surfing eBay just looking at interesting stuff, and I happened to stumble across a seller in Sweden that was selling this pack of 40 Xilinx XCV600e FPGAs. Now if you're not familiar with the part number series of that Xilinx use, XCV means it's a Virtex, and Virtex FPGAs are, in Xilinx speak, but very, very expensive and very powerful FPGAs. Now these Virtex-Es are far from current. They're actually obsoleted by Xilinx, but they are still very powerful things. And I was looking at this auction for 40, and I just couldn't resist it. I had to have them, so I hit the buy it now button, and the total price worked out at about £2 per FPGA. It's two UK pounds, and that's for a Virtex. I mean, I just couldn't resist it. That was so cheap, even though they're not current. And this was about 2 years ago, and the reason why it's been so long between me buying them and actually doing something with them is the package. It's a BGA, and it's a big one. It's a 676 ball BGA. So in this video, we're going to have a look at the package. We're going to have a look at the difficulties that presents in actually building something, and I'll actually try and go ahead and build a development board that houses one of these things. So without further ado, let's get the FPGAs out of this package and let's have a look at them. So here's what these... Oh, fuck it. So here's what these ICs look like when they're delivered. They arrive in one of these like waffle trays, I think they're called. And this one's been held together with a piece of Velcro tape here. So to get inside, all I have to do is just wind off the tape, unthread it, and we should be able to get inside. You can actually see from the underside there, you see all the balls of the BGA devices showing through. Looks nice, doesn't it? So here we go, let's have a look what's inside this thing. Wow, that's an awful lot of programmable logic. How much would that have cost back in the day when these things were actually on the market and current? I have no idea, but it was presumably an awful lot of money. So let's take one of these FPGAs out of here and we'll have a close look at it under a high resolution camera. Right, so here we have the device underneath my camera macro lens. I hope it's in focus there because I can't really see too well myself through this viewfinder. But you can see that the whole device is constructed basically of the die, and the plastic package appears to be soldered onto a very thin PCB. In fact, you can see the traces running out to the edge of the PCB and some very, very fine wires going through to either side there. Now if I flip the chip over, we'll take a look at the other side. Apologies for the lack of focus there, but this camera lens has a very narrow depth of field. Hopefully that's in focus. I'll just stop and make sure that that's better. I just wanted to position the die there so you could see all of the little wires and traces that run out from the PCB to the balls on the underside. It's really quite fascinating to watch. There are of course 676 little balls there. Nearly all of them must be connected. There are some not connected, but they nearly all either run to IOs or power. Power is grouped around the middle, around that little block you see in the middle, and the IOs tend to be around the outside. So now you've seen the underside of this package, you know what a BGA grid of solder balls looks like. I think I'll be able to make a development board out of this. Those balls are 1mm pitch, which is fairly large for a BGA. Lots of headroom there, and at least they're not lead free. These are leaded balls, so I won't have to raise the temperature to a ridiculous level. I should just be able to do a normal SNPB reflow profile. Okay, so let's move on to the design of the board. Okay, so here's the schematic for my development board. It's far too big to fit in one screenshot here, so I'm going to scroll through it. The part for the XCV600e is broken down into many different banks and all sorts of different sections in this schematic because that's the way Xilinx supply it. It would be too big to do otherwise. So across the top here it shows all the different I/O banks. I've got those all going out to different parts of the board here, so I'll just go scroll past all of those. Now the general aim of this board is to provide access to different types of memories, and as well as having some basic GPIO and differential pair access. So if we scroll along, we can see all of the different sections of the XCV600e part, including a whole load of NC pads, as there would be in a big grid. And here we've got a piece of DRAM. It's SDR DRAM. And up here we've got a piece of flash memory. It's a serial SPI flash, 128 megabit. I've used this one before on my Sprite graphics accelerator project, so you might have seen it before. And down here I've got a piece of static RAM, 10 nanosecond. Again, it's the one I've used before on my Sprite graphics accelerator. It's 512 kilobit part, and it's one that I know well. And the rest of the bits down here are just little LEDs for some basic I/O testing. Got the clocks over here. There's 4 global clocks on the XCV600. I've got one tied to a fixed 50 megahertz oscillator, and the rest of them are broken out to headers. Here's the termination resistors for the differential pairs. There's the differential pair header, and the GPIOs up here. Loads of them. You can't actually see it from this header, but I've designed the GPIO part to be a 3. It's not a what is it, 39 times 2, it's 39 times 3 header, with the central row being all ground. That allows me to just to connect on IDC ribbon cables and have every other wire on the cable being ground, which is commonly done for signal integrity. And we've got the power supplies here. There's the 1.8 volt step down buck regulator here, and the step down regulator for the 3.3 volts rail there. And over here we've got an absolute ton of decoupling capacitors, broadly following Xilinx's recommendations for decoupling. Basically you've got different decades of capacitance going up from 47 nanofarads all the way up to 2.2 micros, and a couple of big bulk decoupling ones here, 470 micros. So let's have a look at the PCB layout. It's a 4-layer board, of course. There's no way you could do it in anything less. It would just be completely insane with a big BGA package. That's the multi-layer view. Let's strip that down and show just the top layer, and you can see the the breakout for the BGA there, with the teardrop connections used to the pads to make them more stable. Now if we have a look at the next layer, this is internal ground. So the internal ground is a plane. It's completely unbroken apart from where the wires go through. Layer 3 is signal and traces, power and trace. So we've got some of the traces going through on this internal one, but mostly this layer is for power. It's to get the 3.3 and 1.8 volt supplies through to where they're required. On the bottom layer it's signal, and with a ground fill. Nothing too exciting here, just the signals and some of the oh yes, and of course the decoupling capacitors, which are placed below the FPGA. Let's take a look at that in the 3D view. It's always good for a bit of entertainment. I always have a quick look at this. The best thing that you can get out of the 3D view, in my opinion, is you can see whether your silk screen are overlapping anything they shouldn't be overlapping, like wires, for example. Here I can just have a quick look through and make sure it's all looking okay. You can see top and bottom, and I put a legend here, and that's upside down, but I'm sure you can read it, to show, because I know when this thing's built, I'll need to know which value of capacitor goes on which pad here. So I've just done a little legend here to show which value goes where, and it'll be easy for me to build, I hope. Okay, so that's the schematic and the board layout. Next thing I need to do is get this thing sent off to be manufactured, and I'm going to use PCB Way for this, because I've had good results from them before on their 4-layer boards. They're very communicative. If you engage them in email, they'll tell you the important things that you need to know, like the relative permittivity of the substrate, so you can do differential pair impedance matching, which I've done here. So all of these pairs that you can see running here should be pretty close to impedance matched. So I'll get this thing sent off. It normally takes about 4 weeks to get done, and I'll go and do something else while that's happening. Right, so here's the completed board, blank, as just arrived back from PCB Way, and it's looking really good as usual. I'm really impressed with it, with their service and their manufacturing. Obviously the board is dominated by that big grid in the middle, and on the back we've got the footprints for the decoupling capacitors, and we've got my little legend there for which decoupling capacitors should go where. Everything's looking nice and well manufactured. The differential pair snake traces are all as they should be. There's nothing wrong there. Now I've been through a few of these boards, and obviously the important part is let's get that in focus, is the BGA footprint in the middle, and there were some defects on some of the boards. You'll have to go to my blog page to see the actual defects. But I'd say on about 2 or 3 of the boards, some of the pads have a bit too much overlapping solder mask. The solder mask has actually strayed onto some of the pads. Now, I'm sure I'm seeing this because A, it's a prototype service, you can't expect perfection on every board, and B, because I've got such a huge number of footprints there. If you're just doing just a sort of a BGA footprint with less than 100 pads, you may not see these defects. But if you go to my website, I'll show you some high-res photographs of what the defects look like. Basically, the solder mask appears to have spilled over onto some of the pads, not completely covering them, but just enough to perhaps make the connection to the ball not as good as it should be. I put those boards to one side, and the one I'm going to use for actually reflowing is a perfect one. I put it under the microscope and went over every pad just to make sure that it's fine. So I think it's time for reflow, which should be interesting. We'll see how we get on. Okay, so what I opted to do was a test reflow, just the FPGA on the board, nothing else, just to see whether the process would work before I put the other surrounding more expensive components on the board as well. Because if it didn't work, then I'd have to discard the whole board with some pretty expensive components on it. And it's a funny old world when the Xilinx Virtex on a PCB is one of the cheaper components on there, but so it is today. The DRAM, the SDR DRAM on there is about £7 for itself, and you add up all the rest and it comes to probably about 20 quid's worth of bits. And the FPGA, as you know from my blog, if you've read it, it probably only cost me about 3 quid. So a test reflow was in order. So I did that, ran it through the reflow oven, and then I'll tell you what, I haven't got an X-ray machine obviously. Checking out whether it worked or not is absolutely really hard. You can't see under this thing at all. I had to put it on one side, and sorry if the focus is jumping about there. I had to put it on one side and look at it with high power lights and magnifying glasses and microscopes. I could just see the edge of the balls, and I could see that they've gone flat, which is great. They've flattened at the bottom. That's what should happen. And I checked all 4 corners, and the balls on all 4 corners have gone flat, which pretty much means that they must have all gone flat for it to go down like that. And that's great. So the process works, and I'm now ready to do a reflow of the real thing, and we'll see whether it works again. And I'm sure it will. Now I've tested the process, and we'll get on with it and let's see what happens. So here's the board after reflow, and with all the essential components all soldered onto it. I've stopped at this point in the construction because it's now actually ready to test. I've got the main FPGA obviously in the centre there, the RAM chips around the outside. Everything that I would need to reflow is done, and all of the smaller supporting components are on board as well. What I haven't done yet is the big rows of pin headers here, and on the back I haven't done some of the differential pair termination resistors. Those things are non-essential for testing. I can test enough now without putting more components on board before I know that the thing actually works, because it would just be a waste of components if it didn't work and I'd have to bin the board. I hope I don't, obviously, but it's a risk you take. So I'll go ahead now and connect the thing up with the JTAG header here to Xilinx ISE running in a Windows XP virtual machine, and we'll see if we can program it with a simple design just to test out the connectivity. I'll tell you what, one thing before I move on to the programming, I need to have a rant about my own decision on the order of how I put this board together. I don't know whether you can see that. I'll see if I can move closer to the camera. and hope it doesn't go out of focus. But that grid of decoupling capacitors on the bottom there are all 0402 size, and my God, they were hard to solder on. I mean, I must be getting old or something, because I know I'm getting older. My eyesight isn't what it was. And I did all those manually with a pair of tweezers and hot air gun. And that was totally the wrong way to do it. I got down something like 95% of them, but a couple of them are too close to do without one blowing the other off while I'm trying to point the hot air gun at it. So I'm pretty pleased with what I finished up with. I got, you know, almost everything in there, but boy, it's not pretty if you look at it under the microscope. So I'm not going to show you it under the microscope because it's just embarrassing. What I really should have done in the construction phase is to reflow that lot. I shouldn't have attempted to do it manually. I should have reflowed them and then capped on taped them down and done the other side. But you know, you can't change what's done, so I had to do those manually. And I never ever want to see an 0402 ever again in my life. Anyway, what I went out and bought afterwards, I don't know if you can see this under this fixed focal length lens, but I've got one of these big magnifying things off of eBay, and it's excellent. It really is. It's all plastic. It's not a glass lens or anything, but it's got just enough magnification under it, a nice little LED ring light underneath, to light up you know, your work, and you can place the board underneath it. And I can work with just enough additional magnification there to be able to see an 0402 just like it's an 0603. So I'm actually quite looking forward to trying it and seeing whether it makes up for my eyesight, well, the close focus ability of my eyesight not being what it was once. So yeah. Anyway, enough of me ranting about my failing abilities, and we'll move on to the programming. Right, so this is Xilinx ISE running inside my Windows XP virtual machine. Windows XP runs quite nicely inside the VMware player here. Obviously, you're not running it on a physical box these days because XP is somewhat antiquated. The latest version of ISE to handle this particular FPGA is version 10.1. You can't use any more recent version than that, and XP is the latest operating system supported by ISE 10.1, hence the VM. So I've got my project loaded up into ISE here, and if you haven't seen ISE before, it's basically an old-fashioned IDE with some basic panels around the outside and a little basic editor in the middle with some syntax colouring. I don't use the editor inside there for editing my own files. Obviously, I use something better. I use Sublime Text. I mean, having tried all of them out there, the modern ones, I've used Atom by GitHub, and I've used the Brackets editor by Adobe, which are all very good. But generally, I always come back to Sublime because it's just absolutely superb. And yeah, I ought to register it. Sorry about that. It does syntax highlighting for VHDL, and it's very lightweight, and it's just basically an excellent editor. So back to ISE with this source code here. To compile the source code into a bit stream, you have to go to this side panel here with the processes, and I'm just going to go to implement design, and I'll tell it to rerun all because I've done it before. That's why the ticks are there, but we'll let it run again so we can see the process. XST runs through, which is a synthesizer. It's a small design, it takes no time at all. It's guessed there that my maximum frequency is 112 meg, which is fine because I only need 50. XST's estimate is not the actual final frequency, but it's usually not far off what you're going to get. Map has just completed, and now we're going to the router, which will basically lay out the design on the FPGA. When that's finished, which it will do in a second because it's not very big, as I said, it will run the post place and route static timing analysis, which will tell me whether I've hit my constraints. And I just saw it fly past, and I actually have hit my constraints. So the design is thought to work. Xilinx's analysis is thought to be pretty conservative, so if you hit your constraints, you're pretty much guaranteed a working design. Let's have a look at the design summary. This is a small design, and for me, this is one big FPGA. So I mean, I'm absolutely nowhere near the utilization of 1% of the logic in the design in the FPGA. So it's fairly small, and I haven't actually generated a programming file yet. You have to do the double click on here to do that, which will take the output, which I assume is some kind of net list, and will generate the bit stream from that, which is the binary that can get loaded directly into the FPGA. And it has to WebTalk, because that's submitting stats to Xilinx, which is fine. I don't mind about that. You can configure the target device here by loading the bit stream through Impact. the standalone program, but I'm going to actually run Impact separately so we can see it. I should have it down here somewhere. Yeah, I have, and it's already connected up to my platform USB cable. Now, the platform USB cable that I bought, I got on eBay, which obviously means it's completely non-genuine, judging by the price versus the real thing. But it does seem to work quite well. I do get the odd error from it, which is a bit disconcerting, but it's, you know, small price to pay for being so cheap. I have no idea about the legality of these cheap clones, but they do seem to work. It's connected to this virtual machine, and it's drawn up the topology of my connection to the FPGA here. If you have multiple FPGAs, they can be chained, so you would get a chained diagram here. It's discovered that I've only got one, and I'll tell you what, when I plug this thing in to begin with, it's the first time, you know, checking connectivity, and you see this thing connect to the platform USB cable and discover that your FPGA is there. I mean, that was pretty much you know, a very exciting moment. One of those, you know, fist pumping in the air moments when you know you've actually got your electrical stuff right. So it's already run a few tests here, and I'll just run another one manually. Let's get the device ID out of the thing. Oh, first of all, it's discovered that the ISC has regenerated the bit file, so it wants to load it. Yes, fine. And it's read the ID code out of the device, which is here. You know, the ID code is that it's an XCV600e and it's version 9, whatever that means. It's been quite a few versions by the looks of it. And what I want to do is program, obviously, so I'll double click on here and it will load up the device, and it works. Because the JTAG speed I think I'm running at here is about 10 meg. I'll have to revisit the preferences and check. But it does seem to, you know, work and load fairly very quickly. And I'm just looking at the device here, and I'll embed a screenshot of the device actually running here in the video so you can see it. But the program was successful. I'm happy, and yeah, that's really nice. So here it is, running after being programmed. So you can see here the board is connected up to the Xilinx platform USB cable. The little green light there, it means it's good. It means that the cable has been detected by Impact, and it's been programmed successfully, because, you know, you just saw in the previous sequence I was running the Impact programmer, and there it is running the demo. It's just some flashing and fading LEDs, nothing special, but the important thing is that it proves the connectivity with the FPGA. So just from that little test, I can tell that the oscillator's running. It must be, because it's supplying a 50 megahertz clock. It's being you know, supplied into the FPGA through one of the global clock buffers. The JTAG programming all works, and the connectivity, at least for the GPIOs there that are being tested, is fine, and I've no reason to suspect that the other ones aren't fine as well. So it's looking good, and I think I'll go ahead and build the rest of the board now. So here we are, the last part of the demo. I've put the board together fully now. All the pin headers are in place, and it's there running my PWM LED fading demo, which is the only design I have at the moment. So over the coming weeks I will do more designs to exercise the SRAM, the DRAM and the SPI flash. It's all there for me to play with. I'm happy with the outcome. I've got a decent development board out of this. You know, Virtex boards are very expensive normally, and even though this is an obsolete part, it's still very powerful, and I think I'll have some fun playing around with it. Don't forget to visit my blog site, where you can see the full write-up of this, full bill of materials, design files, all that kind of good stuff. And I hope you've enjoyed watching. Thank you very much.